We'll go ahead and do a few of these, maybe not all of them, but we'll do a few. So for the following motion diagrams, determine the direction of the acceleration. All right, and I'm going to sort of break this down a bit as a process. Some of these, some of these are more straightforward than others, but if you sort of develop a process for how to solve them, they get easy, even if the problems themselves become complex. So the first question that comes to my mind is, where's the starting point? Okay, where's the starting point for these graphs? And the way I think it makes sense for me to think about this is, where is the tail, if you will? Where's the tail of the vector? It's right there, right? So we're starting there, and the head of the vector is, is heading away from it, okay? So why is that important? The way we're going to solve these problems is by thinking about this in terms of the difference between the initial vector and the final vector. So the starting point is right here. The size of that initial vector, vi, and I'm going to sketch it. It's not going to be to scale, but it'll give you the concept of doing vector subtraction very, very straightforward. So we have our initial vector. Let's call it vi, okay. And let's jump down to this fourth one here, and let's call this one VF. That's our final vector, okay? And we want to determine the direction of the acceleration. So in order to do that, let me move this over a little bit off screen. Can y'all see that okay, by the way? Just show up all right? All right, good. Because we're recording this too, and want to make sure that it captures well. So we have VI and we have VF, and we want to know what the difference between those vectors are. So the way you think about that is, well, if you connect VI to VF like such, that I'm going to call that for a moment delta, okay? So that dotted vector, if you add VI plus delta, do you not get VF? You get VF, okay? So what we did is we connected the two beginning points of those two vectors together, and we looked at the gap between them. That's all we did, okay? And so VI, and I'm going to just kind of elaborate a little, plus delta equals VF, or similarly, VF minus VI is equal to delta, okay? Now, final thing is, let's assume delta is related to acceleration. All right. So with that in mind, now I ask you that question again. What's the direction of the acceleration? It's very obvious. What's the direction of the acceleration? Yeah, it's going faster as you go from the initial to the final. And what's the direction of the acceleration? It's to the right, isn't it? It's to the right, because that vector we just decided you have to add delta to VI to get VF. So the direction of delta, our delta vector there, is to the right. Positive. That's right. Exactly. It's positive. It is to the right or positive. I'm going to say to the right. Okay. Let's look at B. All right. What's the direction? The initial. So we start out here because the tail of the vector is right there. So we're starting there. The headed the vector is down this way, right? So let's say the initial, may run out of room here. So let's just transpose the initial, call that VI. Now let's do exactly the same thing. Let's draw our second vector. And I'm offsetting them, okay, a little bit. But technically, you know, the book may say that you actually connect the beginning points directly, you know, overlay them. But I'm offsetting them just because it's easier. It's easier to see what you're doing. All right. And the reason you would overlay them is they're going in exactly the same direction, right? They're going in exactly the same direction. Now, what do I need to do to VI to get to my final velocity? You're exactly right. You're going to take a vector, delta, and you're going to add a vector that goes in the opposite direction, right? Because if you take VI and you subtract that guy there, do you not get VF? I mean, graphically speaking, of course. All right. So, what's the direction of that acceleration? It is left. You got it. Very good. Okay. And I'm going to see to get VI to become VF. Which way? We're gonna have to butt heads with VI, are we not?
Yeah. Is that how you pick which way, I guess? How do you decipher which in the area? You know what I'm saying? Yeah. Is that what that means? You start from there and go
The dots represent zero from what I understand.
The dot is a vector of zero factor.
Okay,
It's not the direction. It's not the starting point. Okay. These vectors start at the tail. Okay. So this velocity, or high rate of motion, and what happens as you go up? You're slowing down. So what would you be okay saying that your direction of acceleration is down? Is down.
So you just look at that by like the size of
How the size is changing. That's right. The change of the size.
that dot acts as a zero. So I guess that's
You're headed to zero. That's right. That's right. And so you can pick any vector and do a similar analysis. And the way that you will want to do these, we're going to have to do these analysis eventually. So that's why I started out doing those. Okay. What's going on with G?
you start to figure out like F, G, direction.
Well, F and G is up and down, right? So the acceleration is down on G, on F, we just decided that, right? What's the acceleration like on G? Where do you start? You're starting up here, right? This is start. Small. Where do you end up? Down here. Is Is the acceleration in the same direction as those arrows? Because you're increasing in speed, right? Okay. Let's just keep moving along here. I think this is, let's keep going and we'll see if, all right, for number 2, for the following motion diagram, determine the sign of the velocity. By convention, we have our velocity going, our motion is to the right, and so our velocity is positive, right? That's our convention. How about B? Velocity is changing. It starts fast. Is it getting slower as we proceed in time? It absolutely is. But what?
Yeah, that's what, yeah, 0 not.
Okay, so just to be clear, that dot is 0 magnitude of 0. That's right. This is where we are beginning our motion. Begin of motion. Okay. I still haven't heard an answer. So what's the to the question? Determine the sign of the velocity. Which way is it headed?
Right.
Why wouldn't it be positive? This is not in it. Just to be clear, this is not about acceleration. This is just about velocity, right? It's just the sign of the velocity. It's slowing down. It's decreasing, but the direction of all those arrows is still right.
Yeah, okay, yeah, I see what you're right.
Yeah. It's decreasing, but it's still to the right. All it's asking for, though, is the sign of that velocity, okay? How about for C? We wore out the right, now we're going left, right? Where are you starting?
Far right.
That's right. You're starting here and you're going this way. It is the sign of the velocity is negative by our convention. That's right. It is negative by our convention. All right. Decreasing. How about D? Same thing, isn't it? See, part three is where we're going to address the acceleration question on these, okay? D, as I would also argue, is negative because we're starting out here, start with the tail, very small velocity, and going faster and faster. E is positive. So that's pretty straightforward based on what we've been talking about, right? All right, good. Three. Now, let's see. Unfortunately, I can't overlay these. Just don't have enough space.
But the 0 always has to be small.
It's all and I think I got C wrong. C is positive because this is slow. This is negative velocity. So therefore, acceleration is positive. It's positive. So this is positive. I got that one wrong. You're exactly right. okay? Right, because velocity here, again, where we headed, we're starting here at a high positive velocity, and we're slowing down. Our velocity is going to the left, so by convention it's negative. If we're slowing down, we have to be having an opposing acceleration. That acceleration is to the right, and to the right by our convention is positive. And that is exactly the opposite sign of that velocity, which is the way it has to be. Otherwise, you'd continue to speed up, right?
It's kind of like a force against.
It's a force against it. That's right.
So what would be a force on B? Where it starts out, I guess your velocity is higher, and it starts to decrease, so it has a force acceleration slowing it down.
You got a brake. That's right.
Okay, so
That acceleration is braking it. And that
so are you choosing the direction of acceleration?
our convention for velocity and for these graphs is that to the right is positive. It's just the convention. We could have done it oppositely, but you have to choose something, right? Okay, so yes. So B has velocity going to the right, positive, but decreasing.
Negative.
That's right. Exactly right. It's negative or to the left. We could even say,
So I guess we're on 3 where it's asking the sign of the acceleration more or less velocity.
this is the sign of the acceleration. That's right. That is this exercise, the sign of the acceleration. It's tricky. You really got.
So you're pretty much acting as an acceleration as your brake.
That's exactly right. That's exactly
So
right.
if you drive like that,
It's not acceleration.
Deceleration, but it's acceleration with a negative sign, right? It is acceleration in the physics sense. It just has a negative sign. You won't find the use of deceleration in these physics books. I don't think they just use convention sign. But yes, in effect, an acceleration with a negative sign is a deceleration. Okay. It's tricky, but you gotta kind of conform your mind to. All right, we did D. D is the velocity is increasing in the negative direction. Therefore, our acceleration is negative because it's increasing. Oh, for E, what's going on with E? You tell me. We're starting at positive. That's positive, right? That's positive. There's no brakes. There's no brakes on this one. It's
going the same way.
and it's continuing to increase. You see, so it's the vectors are getting long, so it's increasing.
So I'm trying to jump back on 2, we're trying to find the velocity. So when you're trying to find velocity, you just focus on the arrows itself,
Yes,
which direction they're headed.
in which direction they're headed.
Right, and then
That's right.
as you find acceleration, you're just pretty much finding the brake.
That's exactly right. Yep. Acceleration is the brake or the accelerator, right? So the acceleration, you have to, in order to know whether or not you're accelerating, you have to know whether or not your rate of change in position with time is increasing or not. And a good way to think about these arrows is that in 1 second, I've gone this far. In this next second, I've gone this far. In this next second, I've gone that far. So clearly it's accelerating, all right? Because these arrows, which we learned from that little YouTube thing that gentleman showed us the last time we met, that was his point, okay? Is that each, you think about the change in position relative to a given increment of time. All right, guys. This is why I wanted to talk about this, because I'm comfortable with that. So it is decreasing. It's traveling to the left, number one. D is traveling to the left. And it's decreasing its speed until it presumably would stop. And because it's traveling to the left, the acceleration has to oppose that travel because it's slowing down. The acceleration is making it slow down, and therefore the acceleration is in the opposite direction. Okay, but the answer to C here is 1D. Are we okay with that? Everyone pretty much agree that's an adequate representation? Okay, good. Let's go to, let's do the bottom one. Construct a motion diagram for a skier moving at decreasing speed up an incline. So he's going up and away, up an incline. It could be very similar to F, right? To F on the previous example, with the exception that there's an angle to it, right? Instead of going straight up. Okay? All right, good. Moving right along here. B, construct a motion diagram for a bottle rocket whose burning fuel causes it to move vertically upward at increasing speeds. Vertically upward at increasing speeds. I don't actually think we did one like that. We didn't do one like that, right? So, but would it be something like?
Would it be G flipped over?
Yeah, basically.
It would be like G.
Turned upside down.
Yes, absolutely. And it's starting out at 0, right? So you got to start at a dot. That's exactly right. Upside down G. Very good. All right, construct a motion diagram for a car moving at increasing speed down an incline. So it's going down an incline. So I would say it's very much the equal and opposite to the ski, right? So it is going increasing speed, although we don't know that it's stopping.
Wouldn't that be G?
BG, right? This is given the information, no more information than we have. It would be very much like G, which is what I tried to draw there. Okay, let me get that. Okay. All right.
Can we do that this spring?
Yeah, we're going to do them both. Yeah, we'll just do them both. All right, so construct a motion diagram for the bottle rocket described in B after its fuel is burned out while it is still moving up, but now at a decreasing speed. So it's still moving upward. So we could say it's starting, so the fuel just burned out.
Vector gets shorter as you go up.
Until eventually it's going to stop.
Turn around and come back down flying.
Turn right back around and come right down, same speed. And you get into wind resistance issues, but to a first approximation, it's going to retrace its trajectory going right back down. And that just flipped the vectors around, right? All right, now, so everybody okay with that one? Let's go on to D. I mean, to the second part of C here. Let's see if I can get this on the screen. All right, a block sits on a, this is a little more involved, isn't it? A block sits on a compressed spring. When the spring is released, the block is first pushed upward at increasing speed. After the block leaves contact with the spring, it moves upward at decreasing speed. Construct a motion diagram for the block's trip. All right.
Wouldn't it be part of the B and the one above?
So I think it's going to be,
Yeah.
well, okay, so it's asking about a two-part motion diagram, number one. So the first part is when the spring is first released and the block is first pushed upward at an increasing speed. So it's going, it says at an increasing speed. So the vectors are getting longer, right? All right. And then we could continue that because now after the block has left the contact with the spring, so this is contact with the spring, and this is after contact has gone. So it moves upward at a decreasing speed, so it's gonna start slowing down, isn't it? Until eventually it stops, and then it probably does what springs do, which is go back and forth. So you could actually put all of that in one long vector diagram, if you will, which would start increasing and then start decreasing. Make sense? Would you have to do, what about the zeros? You would, yeah. You mean right? There's one here, one at the beginning, and then one at the very end. Yeah, I would say you're right. You certainly could do that, and you'd be accurate for sure. Okay. Now let's see what's next here. All right, there's a piece here. We're just going to read through this, okay? Just want to read through this. So there's no exercise here, but it's relevant because we will do an exercise in just a minute. Graphically subtracting velocities to find the direction of acceleration. Consider that, let's see if I can make this a little bigger because it's getting a, in the text refers to the, that is our V initial, okay? We use VI, okay? And V prime in the text is our V final. So you just have to keep that in mind. Label your drawings with VI and VF since those are the variables names we are using. The direction of an object's acceleration at some arbitrary time t can be determined if we know its velocity at two different times separated by a short time interval delta t. The procedure is outlined and illustrated below. Okay. Original velocity. Draw an arrow representing the velocity of VI of the object at some time t. New velocity. Draw another arrow representing the velocity of V F, right, final velocity of the object at a short time interval delta t later, which is also t prime or t final. The velocity change, okay, this gets into the acceleration aspects of it. to find the change in velocity, delta V, during the time interval, delta t, place the tails of V and V prime together. The change in velocity, delta V, is a vector that points from the head of V to the head of V prime, or from the head of V initial to the head of V final. Notice in the figure that at the right that V initial plus delta V equals V final, or delta V is equal to V final minus V initial. Okay, that's exactly what we were doing with those linear graphs in that first section. Okay, determining what V initial is and V final is, and then figuring out the vector required to get you to that V final. That's all we were doing. And this is the same thing. Okay. Acceleration equals the velocity change, delta V, divided by the time interval, delta t, needed for the change. That is, A is equal to delta V over delta t. If you do not know the time interval, you can at least determine the direction of the acceleration because it points in the same direction as delta V. Okay? All right, so that is the procedure for determining direction of acceleration. Now let's see if we have a working problem on that. Let you guys work on this a couple of minutes, okay? Because this, the first one is, I think, relevant. So we can talk about it, but I'm gonna stop the recording here just to save a little space after. So graphically subtracting velocity vectors to find the direction of acceleration. Okay, and again, VI is equal to V, and our VF, or V final, is equal to V prime. And we'll want to label the drawings as such. A ball moves with decreasing speed towards the right along a straight line. Determine the direction of the ball's acceleration when at position A. Okay? All right. So let's just take. So, yeah. So I drew up VI. You see that? My first vector, the initial vector, upstream of my point P. And I drew my final vector downstream of my point P.
Now, wouldn't it be, it says it's decreasing, wouldn't your final vector be smaller?
It would be, and I probably did not do that as well as I should have. I should have made VF much smaller here.
Because I mean, your arrow, what's your little delta? It's
Yeah.
going to point to the center of the circle.
This is delta, and you're right. So but I think I'm not going to erase mine, but you bring up a good point. But I think directionally speaking, it's you're going to get something very close to this. Okay, you're going to get something close to this, except your delta is delta V. This V sub F is smaller, as it should be. It's going to kind of point a little bit more that way, right? It's going to point a little bit more that way, and that would be a more accurate rendering of the problem, of a solution to the problem. So
you put VI and VF at
no. P is here, VI is here. You draw your tangent, right? Your glancing line at VI before P, and then you draw your VF after P. Yep. And then you literally bring those two guys down and you put their tails together. And I tried to, again, as you can look, it's relatively in proportion to the way I drew those tangents. And as you will see, I think about it a little differently than but it doesn't matter, it's the same thing. But I always like to see my vectors add up to the right vector. I've got an initial vector, right, with the tail there and a head there. And then I know I can add my delta by putting the tail of delta to the head of the v sub I, and I bring it down. V sub I plus delta is equal to v sub f, and just rearrange delta is equal to v sub f minus v sub I. You're right. To be religiously accurate, we need a time to convert delta to a. But that's for the purposes of what we're doing now. We can assume a delta t of 1 second or something. God is simply not giving us that information. It's essentially the same as VA. That's right. For the purposes of this, as long as you just remember that if you are ever asked to calculate an acceleration, you got to get your units right, and so you need to make sure you know what the units of acceleration are. Okay. And so, in fact, to that point, and again, v sub f minus v sub I is just delta. I would divide it by delta t to actually get the acceleration, okay? And absent a known numerical delta t value, if you don't know it, just put delta t. Then that is acceleration. That's good enough. Okay? Do you want to do the next one? I think we've got enough time to do. It's not. I think it's a little more straightforward. This is it's a very linear. It's a linear one. So let's go ahead and do that next one. But before we leave, I want to make sure. Are there any questions on this one? Go ahead and get it right. Okay, we'll move on now to the middle one. It says a large mass is attached to an oscillating spring. Determine the acceleration of the mass at point P when it is moving downward with decreasing speed. Okay, a large mass attached to an oscillating spring. Determine the acceleration of the mass at a point P when it is moving downward with decreasing speed. All right, so what's going to happen, and it doesn't necessarily tell you, but can you believe perhaps that the initial velocity upstream of P is going to be higher than the final velocity downstream of P? So in other words, it's starting out fast, but it is slowing as it passes P, and it is moving downward with decreasing speed. So essentially, what they're saying is that V sub f is less than V sub I. That's the way I take that story. Okay, that's my reading of that. So as I said here, V sub I is when it's upstream of P, less than P, which means above it, it has a certain vector that's longer than V sub f. Okay, then you put V sub f and V sub I together with the same starting point. Okay, and to get V sub f, to get your delta, V sub I, again, plus delta, is going to equal your V sub F. V sub F is smaller, okay? So that tells us that we are going to have an acceleration that is counter to the movement of the velocity, to the movement of the ball. It's going to be counter to that. So this is the way I drew that. Okay. V sub I is your long one. V sub F is the short one. Okay. So in order to get from long to short, you have to have a delta that is negative of it. If we're not negative, it would be positive, right? But if it were positive, then that would mean that V sub F is bigger than V sub I, and we decided that is not going to be the case. Move that up just a little bit more. Sure. All I'm looking, and the linear ones are a little bit easier to see because, and I now you see why I try to slightly offset these arrows, because it's harder to see. But V sub I here, okay, is the long vector, right? V sub F is the shorter vector, all right? So in order to get from a long vector to a shorter vector, I am going to have an opposing vector or a negative vector that is equal in magnitude to that delta between the two arrowheads. That's all that's saying. That's all that's doing. We're graphically putting a delta vector here that will get V sub I to equal V sub F. We're having to bite a chunk out of it. That's all we're doing, and that's what a negative vector does. Exactly. That's exactly right. It is slowing down. If by our reading of that problem, the ball is slowing down. And therefore, the acceleration is in the opposite direction of the movement and of the velocity. It's in the opposite direction because we're braking the thing. Okay? And probably what actually is breaking it is the tension of the spring itself. No, it's not speeding up. Now remember, we said the V of I is the starting vector. So it started out fast, but it slowed down because that's what it told us. It said here, look, determine the acceleration of the mass at the point P when it is moving downward with decreasing speed. It tells us that speed is decreasing. See that?
That's how you get your shorter vector.
That's how you get the shorter vector. That's how you get the shorter vector. I'm reading it directly from that problem. The shorter velocity vector, VF, the vector that's after P, okay, based on that, the final vector is going to be shorter than the initial vector. It starts out fast, it's slowing down. Okay. And think about think about a typical spring, a bed spring or something, right? You pull it, and it's going to start really quick, right? It's going to have a huge velocity, but then after it meets its whatever equilibrium value, it's going to start scrunching it together, isn't it? That's going to slow it down. So it's starting out fast and slowing down, and then it would keep oscillating, of course, which would be another level of complexity. So I think we're right. I think we're right on that. All right. The last one's pretty straightforward. I don't think you'll have any problem. The highest point, of course. So she's walking it says north, right? And the speed is 6 kilometers per hour, and it's 4 minutes, right? All right, and then she walks east. So we're going to take a right angle. We're going to go east, right? 4 kilometers per hour for 10 minutes, right? All right. So what is her average speed for the trip? Okay, so that way we would do that. So I'm just going to start working right in here. So it's 6 kilometers per hour times 4 over 60 hours. You see what I did there? Just to get everything to minutes. All right. Plus, or so that we can get rid of the hours, I'm sorry, 4/60 of an hour, because it gave us 4 minutes, plus 4 kilometers per hour times 10 minutes, right? 10 over 60 hours. Okay. And that's going to give us, yeah. Let me do that. Okay. All right. And that's going to give us units of kilometers. And the total time, I'm going to divide by 14 over 60 hours. Okay. And if you do the math there, you're going to get 4.57 kilometers per hour. Okay, so that's just, all this is doing is asking ourselves, what is the elapsed length, okay, at which the lady walked, and then how much time did it take her to walk that length? Okay. So you get the total amount of distance, and you divide by the total time of walking, which was 14 minutes. Okay. I did combine a couple of things there, but
You ain't had me lost any.
okay.
See what you did.
You see?
I did speed 1 and speed 2.
Okay. Yeah. Yeah, I just kind of combined it. But yeah, that's right. Yeah, you can do that. You can do speed 1 and speed 2 and then take the average of those. Is that what you did?
Yeah.
Same sort of thing. Yeah, you get the same number, right?
Yeah.
Yeah. Okay, good. All right, now 6/6, okay? Everybody okay with 6/5? And again, Gerald probably has a better way to do it, where you just calculate the individual speeds.
So the answer is 4.5.
Yes, that's correct. You can do it, and you can do it a number of different ways. There's always more than one way to do these problems. All right, now, so it's 4.57. I'm going to go ahead and erase this. And I'm going to do what, 6/6? So 6/6 says, what is the average velocity for the entire trip described in problem 6/5? All right, so here we're talking about scalar versus vector, right? Speed is a scalar. So we don't care what the displacement is. We added that, we essentially added that length right, to that length. And we divided it by the amount of time it took. And we took, so what essentially what we did is we took that curve thing out and we spread it. We just pulled the rope taut and we figured out how much, you know, what the elapsed time and the time it took, or what the elapsed distance, and then the time it took to get that elapsed distance to equate to the speed. That gave us the speed. Now we're going to need to do the velocity. So what do you do when you want to get a vector? Okay. What I did is I'm like I did that.
So we like taking a step back.
Yes, sir. That's exactly what this is. Yep. That's exactly what this is. Okay. And this is an angle here, theta. And if you convince yourself with some geometry, that's going to be the same angle as that. But this was 0.4 kilometers, right? Because 6 times 4, well, you had to convert the minutes, but that's 0.4 kilometers. That's what I came up with anyway. And this came up to be 0.67 kilometers. Okay. And so this, as you said, goes right back to our old friend Pythagorean theorem. R is equal to the square root 0.4 squared plus 0.67 squared. And that equals, back. And that equals, I got 0.78 kilometers, okay? The amount of time to take that 0.78 kilometers was, well, 14 minutes, right? So to get the average velocity is equal to 0.78 kilometers divided by 14 over 60 hours. Let's see what I got for that. I don't write everything down. So 0.78 times 60. Yeah, okay. That equals 3.34 kilometers per hour. Okay. So and that compares again to the speed is equal to 4.57 kilometers per hour. That's 6.5. Yeah, this is 6.5. So does it make sense that the average speed would be higher than the average velocity? It had to be, because she traveled so much longer. She had to travel a longer distance to get to the same point, because you're only given the same amount of time, right? So that makes sense. The average velocity. So in other words, vectors are a very efficient way to do things. This is as the eagle flies. Of course, you can't always get there that way. Sometimes you have to use a map. Okay. Everybody okay on that one? Yeah, it's pulling out things and that this brings a point, okay, and I'll tell you now, and because we're going to find that as we proceed through this course, what we learn is cumulative, right? So what we learned 2 chapters ago, we'll apply to this chapter, and we'll apply what we did today to chapter 2 or 3 chapters ahead. That's just the nature of the beast. Oh, I may have done it wrong. Yeah. Is that what you got, Andy? Okay. Yeah. Oh. Okay. Oh, I see. Yeah, I understand. Well, I could have got them. I could have had them flipped. Square root. The square root. 4 squared. Can't hit my buttons right.
Okay, yeah, I got it.
Is that okay?
Mine was in great.
Good. Yeah, I'm glad you guys will check me because I do make mistakes. All right. Good. You want to do another one? Anybody have another one? That was probably one of the more involved ones. We'll do maybe 2 more. Yeah, I had someone else ask me about 16. Let's see if I get that.
I don't know why I do this on mine. I rounded everything.
You rounded to the 10th? Yeah. 16, let's see if I have something scribbled here for 16. Let's see if I completely answer. Okay, a bullet leaves a 28-inch rifle barrel at 2,700 feet per second. What were its acceleration and time in the barrel? Acceleration and time in the barrel, okay? Acceleration and time. Is that the one?
Is that solution sheet? This one, that one?
Yeah, yep, that's right. So let's set that, we can set that problem up. So I think you're going to want to get to your velocity first. This is a little bit more involved. So x is equal to 0 when v is equal to 0. Right? So you haven't pulled the trigger yet. The velocity is 0, and let's let x be 0 at that point, right? And then at 28 over 12 feet, the velocity, the final, is 2,700 feet per second, right? All right, so the first thing you probably would want to do, again, there's probably a different way to work this, but I just calculate the V average. It's V final minus VI over 2. And that, of course, you just divide that 2,700 by 2, right? Not yet. We're just getting the average velocity. You want to get your average velocity first, I believe. Okay, because we're going to get the time first. So that's equal to 1,350 feet per second. Now, x is equal to V average times t, or t is equal to x divided by the average. And x, we were given, is however many feet that is. And I didn't calculate that. Oh, yeah, I did. 2.33 feet divided by the average, right? Which we just calculated to be 1,350 feet per second. Okay? So therefore, now just to do kind of a process check, you want your t to be in units of time, of course. So that feet are going to cancel out that foot because it's in the denominator, and that's going to swing your second up such that your units, in fact, will be in units of seconds. And I actually converted to milliseconds. I converted it to 1.72 milliseconds, or 1.72 times 10 to the minus 3 seconds. So that gets your time. I think it asked for that, didn't it?
Yeah, time in barrel.
Okay, time in the barrel and acceleration. All right. So how would we do acceleration? You just pull out another one of those equations. And
I know it's fast.
it's wicked fast. Yep. 2ax is equal to make this a little neater. Stupid board, no, it doesn't want to behave. So 2ax is equal to v final squared minus v naught squared. Okay. So a is equal to I move things around here a little bit. 2,700 feet per second squared, because v naught squared is 0. We decided that, right? Divided by 2 times 2.33 feet. Okay? And that gives you an acceleration, which is a big number, 1.56 times 10 to the 6th feet per second squared. The 2.33.
28 inches by the 12 feet.
That's right. That's what it was. I converted the inches to feet. You needed to do that for consistency of units. Yep. So it asks for the time in the barrel, which we got, and you had to get, you had to use your average velocity. So that's what the operative velocity, and then you use your x is equal to v times t. Velocity times time is going to be a unit of distance, and you plug in your distance, which you calculated from your barrel length, get your t, and then separately you use that 2ax is equal to the difference of those two squared velocity terms. For where? You can use 1.56. What is 10 to the 6? It's 1.56 million feet per second squared. 10 to the 6 is negative. It's not 10 to the minus 6, it's 10 to the 6. So it's cranking. It's cranking when it leaves that barrel.
Yeah, you're going 1,000,000 feet per second.
1,000,000 feet per second. Yeah.
Can you imagine these guys trying to move out in front of that thing?
So you're gonna, yeah, you don't want to be close to the end of that barrel. Of course, it slows down real quick. But that's fast. All right. Tell you what, guys, let's, do you want to do that one more, or you want to call it tonight? Is there another one in particular, does anyone have a question on? So what we'll plan to do before we do the quiz, by the way, the quiz can be compared to the talk about, right? So make sure you go back over everything. Start feeling a little bit comfortable with how acceleration and velocity pair up if you're given a position diagram, like we've been talking about in these different labs tonight. If you're given a position diagram with some arrows that show, essentially that shows velocity, but not increasing, where its direction is, be able to figure out the direction of acceleration. And then similarly for circular motion, that's fair game too. We're not calculating values for that acceleration yet, but that certainly is in the cards for the next go around. Before we do this, anything else? There is one other thing I want to do. This is kind of fun, but let's take a few minutes and do one of the exercises.